All right, so this is section 3, conservation of energy for chapter 6. And I said I went over a little bit on section 2 as well. And so we talked a little, ooh, what is that? Nope. Okay. And we talked a little bit about conservation of energy, the end of the last section. So energy takes all forms. We have mechanical energy, which is movement or things moving, electrical, thermal, nuclear. Anytime work is done, we have an energy transformation that from one form to another. Remember, energy cannot be lost, it only changes forms. So one process might change kinetic energy into electrical energy, another one might change spring potential energy into kinetic energy. But regardless of what happens, the total amount of the energy in the universe must always remain the same. And so this is what we mean by energy is conserved. We can't create it, we can't destroy it. It only changes forms. Oops. There we go. So another example, frictional forces can act on a system like in applying brakes to the car. The kinetic energy of the car moving gets wound up being turned into thermal energy. So the heat produced by friction, because that's how your brakes work. In other situations where all forms of friction can be ignored, then we say that there's no potential or kinetic energy is getting transferred into heat energy because there's no friction there. So in that case, the sum of the kinetic and potential energies is always going to be the same. Okay, and that leads us to this equation that we have for energy, for total energy. So total energy is going to be always equal to the amount of potential energy plus the amount of kinetic energy. And so that's what we mean when we say mechanical energy gets conserved. It means that the total amount of potential energy plus the amount of kinetic energy, if we added those two things together, they always equal the same number. So here's an example. Energy conservation may be used to solve problems, lots of different physics problems. If we can remember, oh yeah, energy is conserved. So for example, energy conservation is used to find the final speed of a set of keys dropped on the floor from a certain height, because when they're at that height, you have zero initial velocity and zero kinetic energy because you're just holding them there. And your potential energy is equal to mgh. Well, when you let go and you drop them, well, then they do have a velocity, they do have a speed. And when they hit the ground, they have no more potential energy, and their kinetic energy is equal to 1/2 mv squared. So I can rearrange those equations and plug and chug. And if I remember that that's conserved, then what's going to happen is that my potential energy I had at the start has to be equal to my kinetic energy that I end up with. And then I can rearrange that equation and solve for Vf. And that's going to be equal to 2gh. Okay. All right. Here's another example of conservation of energy. That an object moving downward through the same vertical distance but following different path will still wind up having the same exact speed at the end. So swimmers at a water park can enter a pool using one of two frictionless sides of equal height. So remember, our final velocity is equal to 2g, the square root of 2gh, if we go back to our previous slide. 2gh. So all it's concerned with is gravity and height, not the path taken to get there necessarily. So you have initial velocity of 0. What is your final velocity? Here your initial velocity is 0 as well. What is your final velocity? And it just depends on, again, the final velocity is going to depend on the square root of 2 times g times h, and that's it. Okay. Changing the initial speed of a downward moving object by a small amount can result in a very large increase in the final velocity. So let's look at, we have a skateboarder coasts on a smooth track that rises from one level to another. If the snowboarder's initial speed is 4 meters per second, as in case 1, the snowboarder makes it to the upper level and comes to rest. With a slightly greater initial speed of 5.0 meters per second, as in case 2, the snowboarder is still moving to the right on the upper level. What is the snowboarder's final speed in case 2? So the first thing we're going to do is we're going to find their initial kinetic energy in both cases, which is 1/2 mv squared. Then we're going to subtract to find the additional amount of energy in case 2. So that is, you have 340 joules more energy in case 2 than you do in case 1. And then you're going to find the final speed corresponding to the energy of 340 joules. Let's look at them. Oh, and that's it. Okay. And that, again, that's just using those equations of 1/2 mv squared and mgh. Okay, so let's look at how they came up with these numbers for this problem. So again, we're just going to use 1/2 mv squared the whole time, since we're talking about kinetic energy in this case. The person, the snowboarder, is moving. So 1/2 mv squared would be 1/2 times 75 times 4 squared, which gives us 600. That's for case 1. For case 2, it would be 1/2 times 75 times 5 squared, which gives us the 940 for case 2. We're going to subtract those two and find out how much excess kinetic energy do I have. And so that excess kinetic energy is what's going to contribute to this guy's final velocity. So that turns out to be 340 joules, and that's equal to 1/2 times his mass, which is 75 kilograms, times v squared. So we're going to solve for v squared, and when we do that, we're going to come up with the 3 meters per second. Okay? All right, so that is it for conservation of energy. Hope you have a great day.